When you look up at the night sky, what do you see? You might spot the moon, a few familiar planets, and a breathtaking blanket of distant stars. It all seems so peaceful, so permanent. The universe appears to be a vast, unchanging stage where cosmic events unfold over billions of years. We feel small, but we also feel safe in our little corner of the galaxy. Our planet has been here for a very long time, and we expect it to be here for a long time to come. This sense of stability is comforting. It allows us to plan for the future, to build civilizations, and to dream about what lies beyond our world. But this feeling of cosmic safety is a beautiful illusion. The universe is not as quiet or as gentle as it seems. It is an incredibly active and sometimes violent place. Out there in the deep, dark void, there are dangers far greater than anything we can imagine on Earth. Most people, when they think of cosmic dangers, picture something they can see. They imagine a giant asteroid hurtling towards Earth, like the one that wiped out the dinosaurs. Or they might think of a supermassive black hole, a cosmic monster that gobbles up everything in its path, including light itself. These are tangible, dramatic threats. They make for great science fiction movies because they are easy to visualize. You can see the asteroid getting bigger in the sky. You can map the destructive path of a black hole as it tears through a galaxy. These threats are indeed real. Astronomers are constantly tracking near-Earth objects to make sure we don't face a surprise impact. And we know that black holes are at the center of most galaxies, including our own Milky Way. They are powerful forces that shape the evolution of the cosmos, but they are also, in a way, conventional dangers. They follow the familiar laws of gravity and motion. An asteroid is just a big rock. A black hole is just an object with incredibly strong gravity. The name itself, vacuum decay, sounds strange and unsettling. What does it mean for a vacuum, for empty space, to decay? We tend to think of a vacuum as nothingness, the complete absence of everything. How can nothing break down? This is the first clue that our everyday intuition about the universe might be wrong. According to quantum field theory, the most successful scientific theory ever developed, empty space is not empty at all. It is buzzing with energy and filled with invisible energy fields that permeate the entire cosmos. These fields are the fundamental building blocks of reality. Imagine the universe has a hidden self-destruct button. This button isn't located in a specific place, like the center of a galaxy or a secret alien base. Instead, this button is everywhere and nowhere at the same time. It is a possibility embedded in the laws of physics themselves. The theory of vacuum decay suggests that our universe might currently exist in a false vacuum state. To understand vacuum decay, we first need to change how we think about empty space. For most of human history, we imagine space as a giant empty container. It was a void, a background of nothingness against which the real things like stars and planets moved. If you could somehow remove all the dust, all the gas, and all the particles from a region of the cosmos, you would be left with pure, absolute nothing. Modern physics, particularly in the last century, has completely overturned this old idea. Scientists discovered that space is not a passive backdrop. It is an active, dynamic entity with its own properties. The biggest revelation came from quantum mechanics, the science of the very small. It tells us that even the most perfect vacuum, a space completely cleared of all matter, is not truly empty. Instead, it is fizzing with energy and activity. So what is creating all this energy in empty space? The answer lies in one of the most powerful ideas in all of science, the quantum field. According to quantum field theory, the universe isn't made of tiny solid particles like little marbles. Instead, the fundamental ingredients of reality are invisible, energetic fields that spread throughout all of space and time. Imagine the entire universe is filled with a set of overlapping invisible blankets. Each blanket represents a different field. Think of a calm pond. The pond itself is the field, stretching out everywhere. If you tap the surface of the pond, you create a ripple. That ripple is like a particle. It can move around, it has energy, and it can interact with other ripples. But the ripple isn't separate from the pond. It is just a temporary excitation of the pond. The idea that empty space has energy might sound strange, but its effects are all around us. This vacuum energy is thought to be the driving force behind the accelerating expansion of the universe. Astronomers discovered in the late 1990s that galaxies are not just moving apart. They are moving apart faster and faster over time. The mysterious force pushing them apart has been named dark energy, and many physicists believe it is simply the energy of the vacuum itself. So, the energy of nothing is powerful enough to be pushing the entire cosmos apart, stretching the fabric of space-time itself. This brings us back to the Higgs field. The Higgs field, which was discovered in 2012, is a perfect example. This field fills all of space and gives fundamental particles their mass. The energy stored in the Higgs field is what defines the vacuum state of our universe. The big question is the current energy level of the Higgs field the lowest it can possibly be? That is the question that lies at the heart of our cosmic drama. To truly grasp the idea of a false vacuum, we need a simple picture. Let's leave the mind-bending quantum world for a moment and think about something more familiar: hills and valleys. Imagine the energy state of the universe as a landscape. This landscape represents all the possible energy levels the Higgs field could have. Nature always prefers to be in the lowest possible energy state. This means that a ball placed anywhere in this landscape will always try to roll downhill until it reaches the lowest possible point, a deep valley. Now let's place our universe, represented by a small ball, into this landscape. In the scenario of vacuum decay, our universe isn't resting at the absolute bottom. Instead, it is sitting comfortably in a smaller, shallower dip on the side of a large hill. This little dip is our false vacuum. It's a stable location. The ball isn't rolling anywhere because it's nestled in a hollow. For billions of years, our universe has been sitting in this dip, allowing stars, galaxies, and life to form under a consistent set of physical laws. The problem is that there is a much deeper valley just over the hill. This is the true vacuum, the state of absolute lowest energy. So how could our universe ball get from its cozy little dip into the deep valley of the true vacuum? In our everyday world, you would need to give the ball a big push to get it over the hill. But quantum mechanics offers a much stranger and more unsettling way for this to happen. This strange mechanism is called quantum tunneling. It is one of the most bizarre features of the quantum world. On the subatomic scale, particles don't always have to go over an energy barrier. They can sometimes go straight through it. It's as if our ball, without any push at all, could suddenly vanish from its dip and reappear on the other side of the hill, ready to roll down into the deep valley. This process doesn't violate any laws of physics. It is a fundamental property of quantum reality. It is a probabilistic event, meaning it's a matter of chance, not certainty. Think of it like this. The universe is constantly rolling the dice. Every moment, in every corner of the cosmos, there is a tiny, non-zero chance that a small patch of the Higgs field will spontaneously tunnel through the energy barrier. It's an incredibly rare event, like winning a cosmic lottery with astronomically bad odds. But the universe is a very big place and has been around for a very long time. All it takes is for one successful tunnel in one tiny spot, anywhere in the vastness of space. If this quantum tunneling event were to occur, a microscopic bubble of the true vacuum would instantly pop into existence. This bubble would be a region of space where the Higgs field has fallen to its true ground state. Inside this bubble, reality would be fundamentally different. The laws of physics as we know them would no longer apply. Once that tiny bubble of true vacuum is born, it becomes an unstoppable force of nature. Because the true vacuum is a lower energy state, it is the preferred state for the universe. The bubble of true vacuum would therefore expand outwards in all directions at the maximum possible speed, the speed of light. It would be a perfect sphere of cosmic annihilation, growing relentlessly and converting our false vacuum into the true vacuum as it passes. It would be the ultimate phase transition, like a shockwave of steam instantly condensing into water. The wall of this expanding bubble would be a zone of incredible energy. As it sweeps through space, it would dismantle everything in its path at a fundamental level. It wouldn't be like an explosion that blows things apart. It would be a process that erases the very rules that allow things to exist. Atoms would dissolve because the forces holding their nuclei together would change or disappear. Electrons might lose their charge or gain infinite mass. The very concepts of chemistry and matter would become meaningless. Everything within our universe would be converted into a chaotic soup of particles governed by a new alien set of physical laws. The universe inside the bubble would be a strange and hostile place. Based on our current understanding of the Higgs field, a true vacuum state would likely not support any kind of complex structure. Our universe would be overwritten by a new and likely sterile cosmic operating system. So, if this cosmic catastrophe is a real possibility, could we see it coming? Could our powerful telescopes or sensitive detectors give us some kind of advance warning? It's a natural question to ask. For most dangers, from hurricanes to asteroids, our best defense is early detection. We build systems to watch the skies and monitor the environment, hoping to buy ourselves time to prepare, to evacuate, or, to fight back. But vacuum decay is a completely different kind of threat. It plays by a different set of rules. The problem is one of fundamental physics, a cosmic speed limit that we can never break. The bubble wall, the leading edge of this new reality, expands at the speed of light. Nothing in the universe can travel faster than light, and that includes any kind of information. There is no message, no signal, no warning light that could outrun the bubble and alert us to its approach. It is the ultimate blind spot in our cosmic awareness. Imagine you are standing on a train track. In the distance, you see the light of an approaching train. The light reaches your eyes first, telling you that the train is coming. This gives you time to step away. This is how warnings work. The signal, the light, travels faster than the danger, the train. But with vacuum decay, the danger and the signal are one and the same. The bubble wall is the light speed event. The moment you could possibly see it is the exact same moment it arrives and overwrites your existence. There is no gap between knowing and experiencing. This is a profound and humbling concept. It means that no matter how advanced our technology becomes, we can never build a vacuum decay early warning system. So we come to the big question, the one that probably keeps you up at night after reading all this. Should you actually be worried about vacuum decay? The short and simple answer from physicists is a resounding no. While the concept is a scientifically valid possibility based on our best theories, the probability of it happening anytime soon is fantastically, astronomically, almost unthinkably low. We are talking about odds that make winning the lottery seem like a dead certainty. To put this in perspective, let's talk numbers. Scientists who calculate the stability of our universe have to make some assumptions, but their estimates are mind-boggling. The predicted lifetime of our false vacuum is not measured in thousands or millions of years. It's not even measured in billions. The current calculations suggest that our universe is likely to remain stable for a period far, far longer than its current age of 13.8 billion years. The numbers are so large they are often written in scientific notation, like 10 to the power of 100 years, a 1 followed by 100 zeros. This is a timescale that the human mind simply cannot comprehend. Think about it this way. The universe has already existed for nearly 14 billion years. Throughout that entire time, in this vast, sprawling cosmos with its trillions of galaxies, a vacuum decay event has apparently not happened anywhere within our observable horizon. If it had, we wouldn't be here to discuss it. The fact that we exist, and that our universe has been stable enough to allow for the slow process of cosmic and biological evolution, is the strongest evidence we have that our false vacuum, if that's what it is incredibly robust. You can and should sleep soundly tonight. So if we don't need to worry about vacuum decay, why do we even talk about it? Why do scientists spend time on such an esoteric and seemingly terrifying idea? The answer is that concepts like vacuum decay are incredibly valuable tools for thinking. They are not just about predicting the end of the world. They are about understanding the fundamental rules that govern our existence. By pushing our theories to their absolute limits, by asking what would happen in the most extreme scenarios, we learn more about how the universe works right here and now. This concept also has a profound philosophical impact. It changes how we see ourselves and our place in the cosmos. The idea that our entire reality might be a temporary, metastable state is a powerful lesson in humility. It reminds us that we are not the center of the universe, but rather fortunate participants in a grand, ongoing cosmic story. This story is far older and will last far longer than we will. This perspective can shift our focus from a sense of cosmic entitlement to a sense of cosmic wonder. We are lucky to be here, to be conscious, and to be able to contemplate these mysteries at all. Thinking about vacuum decay can transform a feeling of fear into a feeling of awe. Instead of being frightened by the universe's fragility, we can be amazed by its resilience. For 13.8 billion years, our universe has been stable enough to create the breathtaking complexity we see all around us, from swirling galaxies to the intricate biology of a single cell. Ultimately, vacuum decay is a reminder that the universe is still full of deep and profound mysteries. We have journeyed to the edge of reality, exploring a concept that sounds like science fiction, but is rooted in our deepest understanding of the cosmos. The idea of vacuum decay, that our universe might be a temporary bubble of reality waiting to pop, is perhaps the most dramatic story science can tell. It speaks of an end so absolute it erases existence itself, a change not within the universe but to the universe. It is a narrative of quantum fields, cosmic energy states, and an unstoppable wave of transformation moving at the speed of light. This cosmic drama plays out on a stage so vast, and on a timescale so long that it challenges our very ability to comprehend it all. Yet, as we have seen, this is not a story that should fill us with dread. The odds of such an event happening in our lifetime, or in the lifetime of our solar system, or even our galaxy, are so infinitesimally small as to be effectively zero. Our existence is the greatest testament to the universe's profound stability. For nearly 14 billion years, the cosmos has held steady, allowing for the slow, magnificent unfolding of galaxies, stars, planets, and eventually life. The knowledge that this stability might not be eternal does not diminish the wonder of this story. Instead, it should heighten our appreciation for the precious and perhaps precarious reality we inhabit. The theory of vacuum decay serves a greater purpose than simply scaring us. It is a powerful lens through which we can view our place in the universe. It forces us to confront the immense, impersonal, and indifferent nature of the cosmos, which operates on physical laws that were not written for our benefit. This perspective fosters a deep sense of humility and wonder. We are the universe's fleeting consciousness, the lucky witnesses to its grandeur. The fact that we can even contemplate such cosmic questions is a gift of this specific, stable reality we find ourselves in, making our quest for knowledge all the more meaningful. Ultimately, the story of vacuum decay is a celebration of mystery. It reminds us that we are still just beginning to understand the fundamental rules of our cosmic home. It pushes us to keep asking questions, to keep building experiments, and to keep looking up at the night sky with a sense of awe. The universe is not a static, finished book for us to read. It is an active, unfolding story full of secrets yet to be discovered. Thinking about its potential fragility doesn't have to be an exercise in fear. It can be an invitation to marvel at the fact that we are here at all, alive and aware in this beautiful, mysterious, and truly awesome cosmos.